Good morning, everybody. Good morning. Good morning. Afternoon. Sorry, afternoon. Depending on where you're at in the planet, right? Or what planet? Maybe you're on a different planet. Nanu, Nanu. Anyway, rather than go through all of this refresher stuff for this job, I said, hey, Grok, considering our previous conversations about me working starting on July 20th for SpaceX at the Bastrop Starlink facility in the ultra pure water and wastewater treatment process as a specialist, provide for me links on refreshers on all skills, equipments, procedures needed for the position to include classes, educational videos, articles for the job activities and duties. So we're gonna start from the very beginning so you guys understand what I'm kind of what I do, and it's gonna be a good refresher for me, so that I'm all ready to go. I haven't worked in ultra pure water in a very long time, but that's really not why they're hiring me. They're hiring me because of all the other experience that I have and my mindset, the creativity of solving problems and stuff, and always asking questions and wanting to figure out do better ways. That's more why they hired me. So your extensive background, grade 4 treatment, grade 2 distribution. Actually, I have a grade 3 distribution now. Military, wastewater systems and engineering, and municipal operations gives you a strong foundation. These resources focus on the industrial and high purity specifics for semiconductor-like and advanced electronics manufacturing, multi-stage ultra pure water production, reverse osmosis, the EDI, which is electrodeionization, ultraviolet polishing to greater than 12.8 mega ohms per centimeter resistivity, and a total organic content of less than 1 part per billion. You'll probably in these videos that you watch with me, you're going to learn what all that means. Complex industrial wastewater streams, potentially including metals like copper, chemicals, and high volume flows, monitoring, maintenance, sanitation, and compliance. SpaceX Starlink role emphasizes operating and monitoring the ultra pure water systems for a manufacturing process and handling wastewater in large scale or closed loops ZLD, zero liquid discharge. That's what ZLD means. Systems. I prioritized free or low barrier resources, YouTube overviews, articles, manufacturer webinars for quick refresh before your July 20 start, plus structured online options and Texas specific resources for process control, math, safety, and regulations. Many cover predictive maintenance, alarm responses, documentations, and quality parameters critical to the high-tech environments. So the first section here is going to be a quick reference, quick free video and article refreshers. And this is where we're going to start. We'll start watching these. And then it's going to be structured online courses. So you can take these different courses, water treatment courses, certification and water technology courses, American Water College, DuPont Water Solutions, webinars, Viola. So and then we get down into Texas specific stuff. And anyway, we're going to start from the top so that you guys don't know anything about it. You can start learning and it'll be a refresher for me. So here we go. Let's do it.
What families are going through today,
Of course,
Katie
crappy
Hobbs
commercials.
just get it. She's lived it. As governor, she balanced the
Katie
budget
Hobbs
without
sucks,
raising
by the way.
taxes, reducing electricity bills, and cutting red tape to build more affordable housing. Katie Hobbs will keep working to make
No,
Arizona
she did not lower
better for
electricity rates. Absolutely did not.
Got safety protocols? Granger has
Nothing but lies.
To call.
It is the purest water you will ever know, and every day chip factories are sloshing their wafers with it. Ultra pure water, or UPW, is an industry term, a term that describes this product quite well. Water with purity requirements so strict you're more likely to win the national lottery than to find a non-water molecule inside it.
Oh, hey, it's right there.
Companies have contorted themselves into pretzels making ultra-pure water, and the bar keeps getting higher year after year. How pure can you possibly get? In this short video, we're going to look at how semiconductor companies make the world's purest water. Ultra-pure water is very pure water. I don't really have any other way of explaining it. It is used in a few industries with high quality control standards. For instance, the pharmaceutical industry uses it to prepare injection and inhaled therapy medicines. Though I should note that while the term is the same, the standards for purity differ between the two industries. But it is in the semiconductor industry where the chemical is most widely used. Fabs use ultra-pure water to rinse wafer surfaces
That's
to
what we're going to be
dilute
doing.
certain chemicals and for immersion lithography. The
We're
average
cleaning
fab
wafer
uses about
surfaces.
2,000 gallons of ultra-pure water each minute, 2 to 3 million gallons each day. Each wafer uses about 2,200 gallons of water throughout its entire production life cycle,
Wow.
spending several hours at a time getting dunked in water rinse system.
All right, so to explain that uses 2,000 gallons. You're like, oh my gosh, they're using so much water. It just rinses off. It goes to the floor. We collect it. We treat it. We take totally clean it and retreat it, and we reuse it. We're not wasting any water. It's the same water. So don't go, oh my gosh, you use more than a city. No, we don't. It's the same water. We just keep reusing it. Chill, you little tree hugger weirdos.
Why does water purity matter? Because impurities can affect the wafer in a number of ways. They can land in between the lines on the wafer design and cause electrical short circuits. Or they can land on the photoresist during the lithography phase and thus cause a projection error on the wafer, kind of like a piece of dust on your camera lens causes a shadow. Or they can cause little nanosecond-long static shocks that affect the wafer's design. All of this affects the wafer yield. Defects from killer particles historically have interfered with the yield learning process, the work of getting from 50 to 90% in yield. It was a critical problem for Intel scaling up its 14nm process node. With this in mind, ultra-pure water producers classify the impurities they can expect to find and remove into several categories. First are the particles. This is the hardest part of the whole process. Any item can shed particles, especially if they're being shaken, heated, or cracked. Pipes and tubing are constantly shedding particles into flowing water, with random bursts that drive everyone crazy. Second, bacteria. Keeping bacterial colonies under control has been historically difficult because they grow and all. Modern cleanroom procedures, however, do a good enough job, and today's companies only have to deal with such colonies in brand new facilities. Third, you want to remove total organic carbons. These serve as food for bacterial colonies, see the preceding point, and can leave unwanted residues on the wafers. Fourth, silica, or silicon dioxide. The element is abundant and can be found in either a dissolved or discrete format. The latter is particularly detrimental to wafer manufacturing. And finally, there's all the other stuff. Metals, ions, and dissolved oxygen. Metals can diffuse into the silicon surface and cause issues, and dissolved oxygen in particular can make bubbles and oxidize various parts of the wafer. Of course, to remove every existing thing in the water is impossible, especially at an industrial scale, but reach for the stars, right? And what producers can
reach for
definitely
the
do
stars.
is filter out everything that can be measured with existing equipment. Even back in the distant past of 2001, when the leading edge process node was 150 nanometers, the limits for ultra purity approached the cliffs of insanity. In 2001, the definition for ultra pure water set the killer particle size at about 65 nanometers, half the feature size. That's about the same diameter as the COVID virus, and 1,500 times smaller than the diameter of a human hair. Every liter of ultra pure water can have only 20 particles of such size. For boron, sodium, potassium, and chloride ions, the expectations are even lower, from 5 to 50 parts per trillion. To compare, the odds of winning the jackpot in the UK National Lottery are 45,057,474 to 1, or 22 parts in a billion, or 22,000 parts in a trillion. You are 450 times more likely to find a winning jackpot ticket than to come across a sodium ion in semiconductor-grade ultra-pure water. And remember, these were the purity standards from back in 2001. As the leading edge advances, the standards continue to ratchet down. More on that later. So how do you get to such insane purity levels? Modern ultra-pure water systems have 3 main stages, which in turn have many little substages of their own, as well as a distribution piping system connecting them. You start with raw water. So you draw this raw water from sources like the city water system, desalination plants, nature, or an in-house recycling system.
Yeah, that's us.
The raw water source can make a big splash. In one infamous example in 2001, Intel suffered an incursion of organic carbons into their ultra-pure water. They traced the source to 100 or 500 pounds of urea amidst 6 million pounds of raw water, or 0.006%. The urea persisted through the filters into the ultra-pure water at about 15 parts per billion. Again, lottery jackpot odds. But this number was still too high, because when the urea was exposed to DUV light during the lithography phase, it decomposed into ammonia and created errors. The urea had always been there, probably due to runoff from nearby farms, but it occurred in unusually high concentrations in 2001 because the rains that summer were at a 20-year low, preventing dilution.
This is a slate truck.
Ah.
Seats 2, fits plywood, turns into a 5-seat SUV.
The first thing to do with the raw water is to put it through the pre-treatment stage. This is where machines and filters remove the majority of the water impurities, suspended solids, chlorine, and other items. Generally, these systems...
This is where I worked. Tube settlers. So we're here in the flocculator areas, we added sand. And this was kind of all in one big area. But yeah, this is pretty much a city water plant. The pre-treatment. And then it goes through filters after this. But this is basically the same concept, everything as a city water plant.
Make extensive use of reverse osmosis.
Except for it's going to be tiny compared to a big city water plant.
Where you put pressure and a non-porous membrane to filter water. This removes the vast majority of particulates, including organics, silica, salts, particles.
Hey, buddy. I was waiting for it to read. Why is my text-to-speech not reading? Just a second. Let me figure out why my text-to-speech isn't reading. Oh, here it is. Oh, it was turned off. All right, it's on now. I don't know why it was off. Oh, it's because I was watching worship music, and I didn't want people like typing in like cunt, twat, on and on and on and on, like while I was away from the room. So anyway. Hey, buddy. Oh, it didn't work. There we go.
Lurker alert. There is a lurker on the channel. Everyone take cover.
Woohoo!
Bacteria, and viruses. After that, the water is degasified and then hit with UV rays. The UV degrades the organics, disassociating them into organic compounds. Then the water is sent into the primary stage. This is often a deionization step, sometimes also referred to as ion exchange, where you remove as many ions as you possibly can. After this, the water is degasified again and then goes through a polish loop. This is responsible for maintaining the circulating water and keeping its quality high. A critical feature is to keep a high flow rate of water through the pipes. A stagnant pipe can allow bacteria to grow, creating biofilms that mess with wafer quality. I do want to note that semiconductor fabs generate their ultra-pure water in-house, so setups and definitions can vary from fab to fab, combining, rearranging, or repeating several processes. For instance,
loop
some
the water.
Japanese fabs include another round of reverse osmosis along with the ion exchange step inside the primary stage. Despite their diversity, almost all ultra-pure water systems share the same processes: ion exchange, reverse osmosis, degasification, and UV irradiation. Monitoring and filtering nanoparticles is difficult, and is especially tricky within a solution rather than on a surface. How do you remove something you cannot easily detect? How do you close this gap in measurement capability, referred to as a metrology gap? The common thing engineers do is measure the water's electrical conductivity or resistivity. The two
Welcome
units
to your
are reciprocal
ultra-pure water treatment class with Delnorin.
of each other. The semiconductor industry tends to measure the latter. Absolutely pure water at 25 degrees Celsius has a conductivity of 0.05501 microsiemens per centimeter, or resistivity of 18.18 megohm per centimeter. This is the benchmark people are going for. Contaminations change water's physical attributes. For instance, a contamination of sodium chloride ions at the level of 0.1 parts per billion lowers the water's resistivity from 18.18 to 18.11 megohm per centimeter. So, metal probes are installed throughout the ultra-pure water piping system to provide real-time continuous monitoring of how far along the water is going through the system. In the case of one reverse osmosis water filtration module, measurements show the resistivity slowly approaching the 18.18 number as it gets processed over time in the RO system. To measure the amount of particles in the water, companies shine a laser through it. The particles would scatter the light.
July 4th is America's 250th birthday. A good time to learn more about.
And they measure that. As a leading edge advance, companies had to use increasingly more powerful lasers with smaller wavelengths. But these tools were most effective for particle size at about 30 to 100 nanometers. Once the killer particle size limit ratcheted down to 20 nanometers, a limit we hit roughly about 10 years ago, engineers realized that there existed no detection tool for consistently detecting sub-10 nanometer particles in low quantities.
And there is a problem also with city drinking water problems, is that laws and people freaking out and becoming obsessed with their health, like at an unhealthy level. They will start passing laws and requirements on the purity of their city drinking water to the point where science can't even measure. The law says you have to have this, but we can't even measure that low. There's no physical thing on the planet that can make that law follow that law, because we have no idea. We can't even measure that low. But people feel good because they passed a new law that made the water cleaner. But it's just stupid. It's just feel good stupidness.
It doesn't mean that they are totally blind. Existing tools can still detect these tiny particles, but it either means having lower detection efficiencies or requiring higher quantities of the tiny particle. Companies are investing in alternatives, and there are some promising candidates. Dynamic light scattering is an interesting one that measures the intensity fluctuations of light as it travels through the sample. The problem is that the killer particle size limit is shrinking faster than these measurement technologies can keep up their measurement advancements.
Exactly.
Unfortunately, this metrology gap cannot be closed with technology. Today, the leading-edge semiconductor industry standard is 10 particles larger than 3.5 nanometers for each milliliter of water at the point of entry into the tool. This is far beyond what's measurable. Thus, companies have resorted to a form of proactive risk control. For instance, the use of a power law correlation to project the contamination level at the target size. First, they measure how many larger particles there are in the water higher upstream in the filtration system. For instance, maybe they find 30, 50 nanometer sized particles upstream. 30 particles might mean 10 5 nanometer size particles based on the extrapolation. This practice is paired with the rigid maintenance of the high efficiency filters and known particle shedding materials like the resins used in the ion exchange system. The SEMI organization has standards for all of this and serves as the source for much of this video, and C93 covers this particular thing. Companies have been using this proactive risk control practice in their ultra-pure water systems for over the past 10 years. Yields haven't crashed, so it seems to have worked. In recent years, a new challenge has arrived as fab engineers now have to deal with nano-sized particle contaminations on the wafer surface, a similar metrology gap now applied to other parts of the manufacturing footprint. In the process of researching this video, I read through entire books about water, written by teams of people. It is amazing to think that more than a significant number of people have spent their entire professional lives studying the physical traits and properties
I want to get that book.
of something as seemingly mundane as really, really pure water.
Ultra Clean Technology Handbook.
It is thanks to them that we can build the cutting-edge technologies we have today. They are the real MVPs. I hope you enjoyed this video. I hope you think of it next time you're in the tub and bathing yourself with that warm water full of killer particles, silica, urea, ions, bacteria, and total organic carbons. Yeah, so relaxing. Alright everyone, that's it for tonight. Thanks for watching. Subscribe to the channel, sign up.
Oh, it's already got the name. I was going to put the name of it there. He's already done it. All right, so that's our first video we watched. Anything in that video you want to talk about? Next is going to be reverse osmosis system explained. General overview, and now we're going to go into what is reverse osmosis? How does it work? What's it about? How to maintenance on it? Troubleshooting, startup, shutdown. Teach me stuff.
Hello, Victor Sanchez with NS Car Wash Systems. Today we are going to be covering the NS RO systems. We're going to create a series of videos that's going to go over the installation, the startup, the preventative maintenance, and troubleshootings of the RO systems. The NS RO system will include a carbon filter. You'll have the NS RO system. This particular unit has 2 membranes. Yours may have 3, 4, 5, 6, up to 10 membranes at most locations for higher volume. And finally, you will have the anti-scalant, which is the chemical and the anti-scalant injection pump that comes with the RO system. In addition to these items, you should also be receiving a polyethylene holding tank to hold the spot-free water, and an NS rinse pump, which will draw water from that tank to deliver to your rinse arch. We're going to be covering the carbon filter. The purpose of the carbon filter is to remove chlorine from the water. The main offender that fouls membranes is chlorine.
Thank you for the thumbs up.
So once this charcoal loses its effectiveness, membranes will foul almost immediately. Basically, the media here will help eliminate chlorine for anywhere from 12 to 18 months. And you could actually...
If you get chlorine bleach going into your reverse osmosis, it destroys them. It destroys the membranes, and it's just throw them in the garbage. Yeah, you do not want so this carbon is to make sure the chlorine, any possible chlorine that was coming in, is being absorbed and used up, but so that when it goes past this into the ROs, there's absolutely no chlorine.
Use a meter, a reading, to measure your chlorine levels to learn when this system is losing its effectiveness. So when you get this filter and you're going to work on the installation, it basically will come with this set of valves here that are basically a bypass, so that you.
This is all just standard like water softener type stuff.
Both of these are closed.
This is like
on your RO.
I don't need to learn any of this stuff. I know all this stuff.
Also need to hook up the back flush. Times you will notice that the water starts to come out clear, and that's when you could go ahead and make the connection from the carbon filter outlet to the inlet of the RO system. Again, this right here is the back flush outlet, and this will come on when the system automatically back flushes itself. But when we're starting up the system, what we're going to do is we're going to plug in the back flushing head into a GFI, and we're going to set the time of day. So we're going to allow the water on the outlet to go for itself, and we just open up this valve. Inside, you're going to hook up a hose to that, and you are as an outlet. Comes with a series of hoses and outlets, and basically you're going to hook up the hose.
I'm really distracted that the man is literally going to die in 8 minutes because he can't breathe. Dude, he needs to go to the hospital right now.
To the outlet of the pump, this polyflow fitting, and then you're going to come over here, and the same section where you hooked up the inlet from the carbon filter to, you have chem in. You remove the fitting there, and you install the fitting that comes included with the kit. Keep in mind, this has a little plastic coating around the nipple there that belongs on there. A lot of people will try to remove it thinking it's just there to protect it, but it is actually a functioning part of this.
It is a filter
Hey, Jonathan Mason.
filtration in micron. We use a 4-inch x 2-foot reverse osmosis filter. We start with a 5 micron going into a 1 micron going into a large chlorine filter going into a pressure.
Hot diggly wiggly. Where do you work at, bud? Pump is
Pump to 110 psi into a.
What application are you working with? Like give us more info. Like, what's your source water? What are you doing? What's the product that you're doing and working with? What's your process? Anti-hammer tank.
Anti-hammer tank full property.
Anti-hammer tank. Are you like a pressure dampening tank? Is that what you mean by anti-hammer tank? Yeah,
Goes
okay.
through the S.
All right.
Particular injection valve, so you want to leave that on there. And you just screw it in. Just on any of these connections that you're making into these fittings and these plastics, basically only wrap about 1 or 2 layers of Teflon tape when you're installing these.
How you doing, BCC?
The expansion of the fittings and cracking and whatnot.
UV light, rocket fuel in her.
UV light.
We're going to go over the electrical hookups for the RO system. First connection that you'll find is 110 volt connection for the back flushing head. When we design these, we call out a 110 volt GFI 20 amp connector on the wall to plug in for each system, and you'll plug that in.
Uh-oh. What was this?
Into a 2,100 gallon tank.
Yeah. Yeah, depending on what your facility is and what your flow rate is going to be. Your all your tank sizes, all of your sizes, your pipes, everything is going to be scaled to what you need to be able to provide for your microprocessing line or your rocket fuel, or any of that. I mean, a small system is going to have tiny little pipes. A little bitty tank might only have a 50-gallon process tank. We make
We take
wonderful
wonderful
showers.
showers.
We take wonderful showers. That's awesome. Yeah. Oh dear.
The RO system for 110 volt. This particular one controls the control panel and offers voltage to control all the solenoids on the system. You also have the 460 volt connection. This one you will hook up to a breaker inside the rinse pump panel, which will feed the three-phase power to the system. While this particular system is three-phase, we also offer a single-phase system. It'll have a 220-volt plug, and it will also have bare wires on it that you could affix the plug that you want or hardwire it to a 220-volt single-phase circuit. You're going to have two sets of cables coming off of the RO system for low voltage controls. The first one is the pre-treatment. So this pre-treatment comes automatically with the wires connected. So if you don't connect this to the wires on the carbon filter properly and also on the anti-scalant, this will stay automatically in backflush because these two wires are connected. So if you don't have it hooked up yet and you want to cycle the system, we could go ahead and just disconnect these wires for the time being. When you're performing the startup, just make sure they're not making any contact with each other. So that is for pre-treatment. And again, you'll have a signal from a low-level switch coming over from the anti-scalant as well. You just took those all parallel together, red to red, black to black. Finally, you have the signal that goes to the holding tank. Inside the tank, there'll be a float there to tell the RO system when the tank is full to shut down and stop producing water. Same thing here. If these two wires are connected, RO is not going to operate. So you want to separate the wires, or you want to connect them directly to the float before you activate the RO system. As I was mentioning before, the final setups that you have is that you'll notice that the anti-scalant has a 110 volt plug on it, and some people want to plug it into the wall. Well, you don't do that. You plug it into a plug from the RO system that
it tells you when to turn it on. It powers that are on or off.
Basically what this does is when the RO system is operating, it has this continuously providing anti-scalant to the system. When the system goes into high level and shuts off, it cuts off the power here so that the pump does not run continuously. As I was mentioning before, this is the level sensor inside of the anti-scalant. So what this does is it lets the system know that you're low, and it shuts down the system to prevent you from operating without the anti-scalant and fouling your membranes. So again, this will hook up in parallel to the pre-treat wire that we've shown there with the connections from the backflush filter and the pre-treatment on the back of the filter. NSRO systems are available in single-phase and three-phase power. This particular unit is a 460 volt three-phase unit. We build these systems depending upon the voltage that you have at each job site. So just confirm that when you look at the cable that the voltage is compatible with.
We have arsenic in the tap water. Hair was falling out before we put the system in. Also, plants were difficult to grow. I am a videographer / drone pilot mechanic / podcaster / I like truth.
// Yeah. For real. Yeah, I mean, finding out and learning, and the more educated you are, the more educated you are, the more you find out you know very little. People get into that comfort zone of thinking they know something so well, and even if they do at this moment, that industry and that information becomes old really fast as things begin to evolve, change, move forward without you. You have to keep learning.
The site voltage. So when you hook this up, the majority of the time what we would do is that we provide a connection inside of our rinse pump panel. The rinse pump panel has a main disconnect built into it, which will act as the disconnect for the RO system. Inside of that rinse pump panel, there is a breaker feed where you will hook up these wires and hook it up. In the event that this is hooked up to it's a designated breaker, you would want to put in a disconnect and connect this to a disconnect, have a disconnect on the wall for the RO system if it's not hooked up to a rinse
Wait a
pump.
minute. I'm confused here. You said you have a 2,100 gallon tank. Is that at your house? But then you were saying UV light to make rocket fuel. Are you talking about at work for rocket fuel? Or are you saying, I'm trying to understand why you would need ultra pure water instead of just RO water? Why you would need ultra pure water in a home?
Yes.
All right, I asked 2 questions. I'm sorry. I should have asked better. A, we're talking about house, no home. Okay, good.
No
Okay,
home.
good. Okay, good deal. I asked an either or, and then you gave me a yes. So I was like, oh crap, I asked a bad question. Okay.
Now,
Cool.
on the single phase panels, it'll be a single phase 220, and it will come just like this, bare wires. So if you want to use a wall plug, you could go ahead and adapt it to a wall plug, or if you want to go ahead.
All right, blah, 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 blah. Blah, 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 blah.
And burning out the pump. Of the water that's being fed to the RO. So these are the functions that you have on here. So you have.
Go back to here.
So the space shuttle fuel is in all humans on Earth, comes from the water.
There you go. Yeah, everything. Water is the basis of all life. And where does fuel come from?
Go to the system and it's going to be powered off. Right now we don't have any power going to the pump, so you're not going to hear any of that because it would just drown out our narrating. So what you're going to do is you're going to hold the start-stop button down for 2 seconds, and you'll notice that there is a start delay. And the reason for that is because this solenoid opens and we allow the city water pressure to fill the filter and fill the membranes and get water over to the pump so that the pump doesn't cavitate on startup and go into a low pressure condition. So once you have the RO running, it'll be the permeate high flow alarm.
You know, I'm wondering, his breathing might be totally normal. I mean, how many of us have like this super sensitive microphone that far away from our faces? Maybe we all sound like this poor guy that sounds like he's dying. If we could hear ourselves that close, you know?
It's showing that it is actually full. And then you'll have the permeate TDS, which will show you the parts per million of the permeate, which is the RO rinse water. This will cycle as this is on. So
I was listening to not G. Gordon Liddy, Mark Levin.
A chick made it. I could look it up, but so can anyone. It is the most toxic fuel ever made.
The rocket fuel. Mark Levin had this breathing disorder, or his throat or something. It was just, and they upgraded the microphone to like this crazy EDM or whatever microphone that was, and then you could hear like spit dripping off his teeth in the back of his mouth. It was gross. I just stopped listening to him. I'm like, I usually listen to but I just can't listen to your going. I'm like, stop. I just can't. It's just gross. Just so gross. So I listened to thousands of hours of this podcaster, and then they upgraded their mic, and I just stopped. I'm like, I can't do it.
It will give you RO runtime of how many hours the system has been in operation. And you'll also get an inlet TDS reading on here, which will let you know the total dissolved solids of the water that's being fed to the RO.
You know where
Do
the
you know where the
solid
solid fuel for the space shuttle went? Takata airbags.
Takata airbags? I don't know what Takata airbags are.
So these are the functions that you have on here. So you have these arrows, which...
Was Takata airbags the answer to... Are you answering your own question? The solid fuel for the space shuttle. And you're saying that they use that fuel for whatever Takata airbags are.
There's no need to operate those at all. And also the manual switch down here is just a switch that you could hold down to bypass all of the solenoids and all the protection that the RO has to make it run, to force it to run manually. We don't recommend touching any of this.
Okay.
And your steering wheel.
Only thing that you need to do is turn the RO system on and turn it off. Here we're going to go over the RO system control panel. Basically, you have the on-off switch here. You hold it down for just a second, and this will start up the RO system. You'll notice that it has pump delay here. Basically, what's happening here is...
All right, we don't need to watch this. This is super boring.
You have everything connected, and you're getting ready.
I don't need to know how
to... does not have an
to...
adjustment on it, but the concentrate, recirculation, this valve...
Hey, thanks for the follow, buddy.
Closed. This valve is going to stay closed for the duration of the...
I gotta turn it off.
Hold up, everybody. Come on. Oh, no. We got a follower. We got a follower. Hold up.
I had it in that other mode where and it blocks the follow thing.
We need to watch this. It cures insomnia.
Okay, that's fair.
The operation of
hey,
the
code, buddy.
System. We do not like using this particular function of the RO. We prefer to go without. Then on the concentrate flow rate, this one, you will make sure that the valve is closed. And again, you will go and do 2 turns out. And you can measure the turns by a little hole it has here that has a Phillips screw to secure the lever. And you can measure the turns there. So then you'll go ahead and start up the system. We're not going to start up the system right now because it'll make a lot of noise and you won't be able to hear us over the noise. So we're going to explain the functions here.
So why don't you like do a startup, do all this, fine, but then run it, mute the thing, and do a voiceover, an audio voiceover with some video software. That would be actually super helpful.
So you've got the pump pressure. So with that valve open, pump pressure is going to be right around
At Code
80
Zealot,
PSI.
so does ivermectin.
For initial startup. So you want to see that at about 80 PSI.
Because it might explode or something.
Another way to control it too, pump pressure, if you can't get it off there, you also control the concentrate. But what's going to happen is that you're going to adjust the concentrate to achieve the levels that you want here on this side. So this basically tells you on this side the gallons per minute that you're producing. This tells you the gallons per minute that you're discharging.
Wasting. Yeah.
So this particular system, being a 2-membrane system, is going to produce right around 2 gallons a minute. Anywhere from 2 to 3 gallons per minute is what it's going to produce, depending on the actual water temperature. So you're going to make adjustments here to get this somewhere in the 3-gallon neighborhood and to get this right around the 6-gallon neighborhood. So basically a 2-to-1 rejection rate. As you're doing those adjustments, you're going to notice that the pressure on the pump is going to fluctuate. So it's a balancing act. And basically, when you have new membranes, you want to run the RO system, the membrane pressure, or the permeate pressure, the pump pressure, at about 80 PSI. The max pressure that you want to run on these membranes at any given time at the end of their life cycle is about 150 PSI. No? So once you've made the on adjustments to get the RO started up, you're going to want to adjust the pump pressure and you're going to want to adjust the concentrate release on the gallons per minute on that. So basically what we're going to do here is we control the pump pressure. It is going to control the amount of permeate water that you're making. In this particular case, with the 2-membrane RO, it should be generating right around 2.5 to 3 gallons per minute.
He already said that.
So you're going to want this gauge to be sitting right around there, or just right below the 3 gallon per minute line. This one is always going to remain closed, as we said before, so there's going to be no reading on that one. This particular gauge here, since we're want to do a 2-to-1 ratio, this one is going to be right at about 6 gallons of rejection per minute. So you're going to set it there. So as you start making adjustments to these, it's kind of a balancing act. So once you get that set up, you could go ahead and you could twist the valve to reduce pressure or open the valve to increase pressure. So counterclockwise open, clockwise close. And you just want to make sure that you're achieving the pressures that you are looking for, which on this particular one is just below 3 gallons a minute, 3 gallons, and the 6 gallons per minute on the rejects. So you'll be playing with that. And then the pump pressure will fluctuate depending upon water temperature. The lower the water temperature, the higher pump pressure that you're going to need to produce the water that the system's designed to produce. So your operating PSI will vary depending upon locations. Warmer weather, lower PSI. Colder weather, higher PSI. You can operate these systems all the way to 180 PSI. Do not exceed the 180.
He said 150 earlier.
So
I
we've
saw
gone
they
over the
redid
pump
that
pressure
thing.
gauge. Now we are going to talk about
They
the
really don't
concentrated
want
pressure.
photo editing.
So
They would
basically,
rather
the
redo a
concentrated
5-minute
pressure is gonna
conversation
be
to change one number
less than the pump
to
pressure
edit
by
anything in
about
this
50
video.
PSI. So basically, this is a 2-membrane system. The more membranes that you have, the bigger the pressure differential will be. So you take note of your pressure when the system is started up and it's running optimum. And as you see the pressure start to decrease on this pressure gauge, that means 2 things. It means that you need to clean the RO, service the RO membranes with muriatic acid flush, or replace the membranes. First, we always try to do the muriatic acid flush and then see how our pressure differential is after that. So the 2 gauges below, this particular measures the filter in pressure. So this measures before this 5 micron filter here, and this one gives us the pressure after the 5 micron filter. So let's say you're getting 40 psi, and this one with a new filter should read 40 psi. As this filter goes through its life, it'll decline, and
That'll go
you'll
up,
see it
that'll go
drop
down.
between in and out pressure.
Yeah.
Once that out pressure difference is more than 10 psi,
Differential.
it is time to replace that filter.
Got it.
We generally recommend replacing that filter every 30 to 45 days, a rule of thumb. But you can go longer if you notice that your pressure differentials are in the right parameters. Again, if it's greater than 10 psi, it's time to replace it. Another good rule of thumb is doing it every 30 to 45 days, is so that you can go ahead and get the anti-scalant system back up to speed, fill it up. When you have your power connected, you're going to have to check the rotation of the pump. And basically down here, you'll notice that it shows you an arrow for the rotation. And this one is the rotation going in this direction. So when you start up the RO system, you'll start it up, and then you'll look at the top of this screw here, this
on the motor.
this mount, and you see what direction it's turning. If it's turning, it needs to be turning in this direction. If for some reason it's turning the opposite direction,
Change 2 wires on
need
your
to
pull. Yeah, it's easy.
open up the panel
3-phase motors.
and basically take these 2 wires
Switch them out.
and switch them from each terminal, and that
Yep.
will switch the rotation of the motor. This
Yeah.
only applies to 3-phase. If you have a single phase,
Yeah, it doesn't matter.
The motor will automatically spin in the correct direction.
Yeah.
In the previous video, we went over the settings for the gate valve on the pump and also the concentrate flow. So 2 turns out, and yes, that should help evacuate all the air from the system. But basically, before you make the adjustments, the final adjustments that we discussed, you want to make sure that these valves are flowing pure water and that you don't have air bubbles. So you definitely want to watch that for that. And once you see water's flowing and no more air bubbles, then you can go ahead and proceed to making the adjustments as we had discussed, depending upon the amount of membranes that you have. Basically, once we have the system started up and we've had all the adjustments made on the pressure for the membranes, we want to go ahead and look at all the fittings on the RO system to ensure that we don't have any leaks. So you'll definitely want to look at the interconnections between the membranes, all these polyflow connectors on top and on bottom. You want to look at the back side where all the gauges are located, and the flow meters. All that you want to inspect and see if you have any leaks. And of course, if you do, you want to go ahead and correct those leaks. You'll want to check the inlet side. You'll want to check the pump outlets, the pump inlets. Also, the carbon filter could also have leaks if you haven't connected the bypass valve correctly. So you want to check all that out and make sure that we do not have any leaks. Now we're going to talk about filter replacement. As I'd mentioned before, you want to take a look at the filter in and filter out. If you've got more than a 10% differential on the filter outside, say you got 30 psi on this side and 20 on this side, it's time to replace this filter. Real simple. Use the filter wrench that's provided and spin it right off. Remember, this is going to have water in it. So
this is very specific to his company's thing. It's not.
And you get into the quarter turn.
I'm looking
for.
I mean, some of the information is actually good.
That we can install a hose on.
But when it gets too much into the minutia of his particular company stuff,
an acid bath that will help remove any scaling. A 5-gallon bucket that you could fill up with water, and then we'll give you the ratio that you need to use for the particular RO. For example, this one, for every gallon of water, you would use 1.33 ounces of anti-scalant. So basically, we would add that and then fill this as needed so that you're putting in the proper ratio into the pump. As we had mentioned before, getting the proper ratio of anti-scalant with the RO water mix is imperative to make sure that the injection performs to keep those membranes as best possible. All
right, we're done with him. I mean, he's totally good information. You know, very specific to his own company stuff, and that's very good. If you're buying his stuff, you are going to want to watch that video. Now we're going to learn about electro-deionization water treatment systems. This is going to be a clear product process overview of the chemical-free polishing step used in the high purity system. Electro-deionization. Now, this is just RO, reverse osmosis, is one part. Electrodeionization is another part. There's several different processes that we're going to be doing, and this is just one step. After it comes out of your factory, you're going to have to raise up your pH, drop out your clarifiers. You're going to have to get solids to come out the bottom. You're going to have to sludge press. The clear water comes off, goes in another stage. When you're adjusting everything back the other way with the pH and everything, and then it goes into your pre-treatment, and then it goes into your RO, and then it goes, so it's a long. There's several. So this is just one little step. The EDI, electrodeionization, is one of those steps. So all of this stuff is just one little part of the huge long process. It's not just this. It's not this, you just learn this system and you're done. This is one of like 8 things in a chain that happen. And if this goes bad, that could cause things three chains down, or 3 links in the chain down, to start to go bad. Or this is starting to go bad. Well, it's probably the EDI system is doing this. And you got to just become instinctual on your equipment, your factory, your setup, so that if something, that pressure gauge is doing that, well, that means that this is happening, or that over there is happening. And then you have to make a, and then you're constantly checking everything to make sure that everything is in specs. And then at the same time you're doing all that, you're trying to think of, how can I make this better? What can I do to even improve what we're doing here? How can I get cleaner water? Yeah, this is what the factory says we can do, but we can do better. What ways can we do to make this better? So your mind is going 12 hours a day, day after day after day. There's no shutdown. There's no sitting back, putting your feet up on the desk and chilling, waiting for an alarm to go off on a SCADA system. No, you are constantly on edge the whole time. Oh my gosh, this company is really hyping their stuff. You want to remove all gases, even dissolved oxygen in the water. Hey Dizzy, Drizzy Dizzle. Drizzle my dizzle, yo, shizzle. How you doing, buddy? Hey, thanks, bud.
I got you tabbed.
Whoops. He dropped in yesterday. I want to see if he's streaming. He is. Hey, I'm gonna pause my thing here. Sorry. I want to share with you guys him. Here, you guys. So if you guys want to go check him out, I'm gonna share the URL over on YouTube and X and Rumble and everywhere. Slight distraction, but that's all right.
Rain like this would fetch a fortune.
I think I'm in a good place. I need to craft weapons.
All right, let's get back to it. All right. Ba-bum, ba-bum, bum, 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 ba-bum, ba-bum, bum, bum, ba-bum, 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 ba-dum, ba-bum, ba-bum, ba-dum, 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 ba-dum. Oh my gosh, this thing is going on and on. I mean, there's a good info in this. From low feed or high discharge pressure, okay? Pressure gauges. Wetted, that's good. I hate dry gauges. Oh, pressure transducer, turbidimeter, right? Conductivity and resistivity sensors. Where are those? There is, okay. I can't see with my eyes. There's a pressure sensor. There's some like rotor valve controls. What is this? Oh, those are just handles for ball valves. My eyes, I can't see. It's fuzzy. All right, flow meters are here. Paddle wheel flow meters. All right. Oh, this is a transmitter. Sorry. It takes the signal from this and then sends it to ORP and pH probes. Magmeter flow sensors. Differential pressure switches. All right, now tell us more. It's not going to. Ultrafiltration.
So, is this a filtration for drinking your pee in space?
No, I'm working in the wafer production for the Starlink satellites. Also for what you're gonna buy. Say if you want to buy a Starlink system that has the dish and the controls and everything, or the solar panels they're starting to make, or they're not starting to make. They're really working hard. It's this massive facility just to the north of the Starlink facility, where they're going to make their own solar panels too. So when you buy a Starlink satellite system, you'll get the boards, the chips, and everything that are in that will be from my facility. So I have to make the ultra pure water for them to make the wafers. They're pressing all the wafers together and the cardboard traces and all of the stuff, retreating that water and bringing it back around so they can keep if any kind of impurity in the water messes it up, and you'll start getting lower performance in your satellite system. But yeah, that's where I'm starting out, is in that system. And then of course I will be looking for advancements as the years go on. It might be moving down, to launchpad type stuff. I don't know. But this is where I'm starting with SpaceX, is in the Starlink facility, and we're gonna see where it goes. Really stoked, really stoked. Tank level switches, speed pumps.
Oh, we have the new wafer plants from Twain down the road from us.
Twain? Oh, Twain? Is Twain a company? Twain, the word is and meaning two or a couple.
Twans.
Twans. Twans is the name of the company? Twans. Refer to
Taiwanese.
Oh. All right. All right. Got it. Oh, okay.
Dog haters.
Got it. Oh, they got feedback. I don't think we need to watch this video anymore. It's just them showing the component. I mean, it's useful, but again, I'm more of a wanting to study the processes and stuff for my needs here. So we're making a little thing where all the different videos are going to be listed here as we watch them. All right, what's our next video? Ultra pure water systems in semiconductor manufacturing explained by Axion Water. Detailed stages, the pre-treatment, the RO, the EDI. The last thing was the EDI. The ultra filtration, the ultraviolet oxidization, and the final processing. This should be a really good video. Key components, quality specs, resistivity, total organic compounds, particles, bacteria, silica. All right, this one should be a really good video. All right, what do we got here? How do we watch this video? Is it just going to be an inline in the web page video, or is it an article? Ultra pure water systems manufacturing. Follow us. Ultra pure water. Or I guess I'm going to be doing some reading, and we'll be looking through this. Oh, it's just an article. Oh man. Well, it looks like it's got a lot. Let me just bookmark it right away then. Okay. Ultra pure water systems produce. Is that zoomed in enough? Probably. Produce water with resistivity exceeding 18.2 mega ohms per centimeter. It's mega ohms, right? Per centimeter at 25 degrees Celsius for semiconductor manufacturing processes where contamination control determines chip yield and performance. You want a crappy microchip on your computer? Well, make sure your water is perfect. If you want to be like the leading edge, awesome, best chip maker all on the planet, then you want me working for it. Yeah. I've got all kinds of things zapping on my phone here. What's going on here? Oh, somebody just sending me spam. Oh, we've approved a $29,000. Screw off. I don't know why these people block contact, delete, report spam. There we go. I get 3 of those a day. They wanting to give me a loan. I'm like, go away. Semiconductor fabrication facilities consume 2 to 4 million gallons of ultra pure water daily. No, they don't. No, they don't. They could if they just like put all the water down the drain that they use, but they don't. They reuse that water. So yeah, they don't use 2 to 4 million gallons a day. That's just lying. That's trying to be like dramatic. With advanced fabs using 4.5 to 7 liters per square centimeter of processed wafer. All right. Well, okay. Contamination from inadequate water purity causes defects that produce manufacturing yields or reduce manufacturing yields, with water-related issues contributing to significant water failures in the sub-7 nanometer chip production. This guide explains ultra-pure water system technologies, critical quality specifications, semiconductor applications, and key operational requirements. All right, this is going to be really good. I don't know how they share all that information in just 3 pages. What is ultra-pure water? Ultra-pure water is water purified to achieve resistivity of 18.2 mega ohms per centimeter at 25 degrees Celsius with total organic carbon, TOC, below 1 part per billion. Particle counts under 1 particle per milliliter. Is that milliliter? For particles greater than, that's not right, microliter. Yeah, it's got to be microliter. For particles greater than 0.05 micrometers. All right. And bacteria levels below 0.1 CFU microliters. Cubic feet. I don't what. I hate acronyms. I totally hate acronyms. Let me look up here. In water, in ultra pure water, what does the unit CFU/ml stand for? Colony formation unit per milliliter. Oh, bacteria, duh. Sorry. I was concentrating on reading and not fumbling over my words and forgot to pay attention to the words I was reading. Colony formation unit, bacteria, duh. This purity level exceeds standard purified water by removing ionic contaminations, dissolved gases, organic compounds, and particles to parts per billion concentrations. Regular tap water measures 0.005 to 0.05 microohms per centimeter resistivity. So you can have 0.05 would be as dirty as your tap water would be, microohms resistivity. While reverse osmosis achieves 0.1 to 1.0 micro. Wait a minute. What am I looking at here that's backwards? Why is that higher than the tap water number? The tap water number should be much higher than the reverse osmosis number. Ultra pure water, semiconductors, industries, specifications defined, blah, blah, blah. So, resistivity, they want more than 8.2 microohms per centimeter. TOC is less than 1 part per billion. Silica, the dissolved form in this range, 0.2 to 1.0. Silica in the colloidal form, 0.3 to 2.0. Nanograms per liter. I don't know what that is. I wanna figure that out. What does ng per liter stand for? Yeah, nanogram per liter. All right. So I know my units. Get off my back, man. Just that I never use them. I'm like, seriously, you can go 30 years in water treatment, never use a nanogram per liter. When you get into this kind of water treatment, then yeah, you got whole new things to brush up on. Why is ultra pure water critical for semiconductor manufacturing? Ultra pure water is critical because semiconductor wafer surfaces require contamination-free processing, where even microscopic impurities cause critical defects in sub 7 nanometer chip production. Smaller than 7 nanometers. You're making chips that are just like under the microphone or under the magnifying glass to even see what you're doing. A single 200 milliliter wafer, 200 millimeter. So that's a pretty big, that's 200 millimeters. That's a centimeter would be 20, so 20 centimeters. So that's like a motherboard size. I want to convert it to inches just because I'm a dork. 200 millimeters is how many inches? 7 and an 8. So a 7.8 inch by 7.8 inch wafer. Okay. A single wafer, single 200 millimeter wafer requires 7,600 liters of ultra pure water for cleaning processes. So let's convert that to gallons. What the heck was this liters and milliliters crap for? 600 liters is 1,500 gallons. That's a lot. I mean, seriously, that's a lot. Because what you're doing is you're having a wafer, that 7.8 inch wafer, and you do what you need on it, right? And then you until it's like perfectly clean. And then you're putting on another wafer on top of it that you've cleaned, and then you're pressing them, and then that's got your copper traces in it, and then you're compression, and then you're putting another layer on it, and that's got this like little holes and little things in it that where all the little components are going to be, and then that gets all superwashed, and that gets superwashed, and then so you end up with like layers of these wafers that make a motherboard. And then each step, you're got this ultra pure water cleaning it, because any tiny little anything will screw it all up. So you're in like these super clean environments with like spacesuits and arms and stuff, because you can't even put like air in the room, that kind of a thing. Whoa! I was reading the thing. Why'd you just go away? That was weird. It just scrolled me to the bottom. I didn't do that. So as the water is going over like the copper traces, you get a bunch of high concentration copper
what a cool job.
in that water.
Nanogram is used as a measurement in drug testing for weed THC. In your body that naturally has THC in it, but in very small amounts.
There you go. Yeah, it's amazing what is in that. I mean, like, okay, so you go back 600 years and you're like, this is salt. Yep, that's salt. Ooh, that's salt. But you go forward 600 years and they're like, well, on the microscopic level, the ceramic of the bowl that you were in is slowly sloughing off a silica-based blah, 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 and at measurements exceeding 500 millimicroohms or whatever, you can die, and it shortens your life by 0.3 hours per lifetime. I mean, it's like, you'd be amazed by what is in your normal life. What you breathe in normally, you'd be like, oh no, it's normal. Calm down. Your body is not like the tiny little a molecule of something coming and bumping into you. It's not going to kill you. Chill. You're guess what? People have been dealing with poop on their hands working on the farm for thousands of years. Calm down. But yes, it's in your body naturally. All kinds of stuff are in your body naturally. But yeah, the finding that balance of what is healthy and what is an overreactive narcissistic freak out. Our culture in the last 20, 30 years has probably been a little too far on the freak out level. They just need to chill, man. Just eat some veggies and meat. Have some eggs. Drink some raw milk. I mean, stop being a pansy and taking a vaccine for everything and then becoming allergic to everything on the planet because you were scared of getting sick. You gave yourself a vaccine that made you sick to everything. Good job. Good job. All right. Anyway, quit distracting me, show. Gee, many crickets, mister. All right. Where was I? Contamination impacts manufacturing yields. Oh, we talked about that. Oh, no, we didn't. Directly, ultra pure water improves production yields and reduces the defects with proper water quality, maximizing semiconductor productivity. That is me, maximizing productivity. That's what I'm going to be doing. Making sure the chips and the wafer boards and everything that is being made in the Starlink facility are going to be keen quality. And the thing about that is it's going to get better and better and better as we are able to measure things. Like right now, you want the purest water possible, but you can't even measure that low. So you're just extrapolating and guessing because because you're like, well, if at this it gives us this purity, if we do twice as much, it should make it twice as clean. If we do twice as much, just make it twice as clean. If we do twice as much again, make it twice as, and then so you start like just guessing at what you're actually producing because you can't measure it because there's no equipment that can measure it that pure. That's kind of like where that's how you just guess, because technology isn't there yet to be even measure like a 0.0001 per megatrillion. I don't know what's above trillion. Dodecagon or something. I don't know, some crazy made up number. But anyway. Single fab investments range from 1 billion to 4.6 billion, requiring zero defect water to protect capital and expenditure. Advanced node requirements for 3 nanometer and 2 nanometer chips demand stricter purity specifications with a total organic carbon below 0.5 parts per billion. So up here, this was less than 1 part per billion. And this was talking about these less than 7 nanometer chips, or 7 nano, what was it? 7 nanometer chip production. Down here, we're talking even smaller chips, 3 to 2 nanometer chips. Now, instead of a less than 1, now they need less than a half. So it's even way more purer because now you're making the chips even smaller and smaller and smaller. And pretty soon a hydrogen atom, oh no, there's a hydrogen atom in there. It's gonna, ruin everything. Of course you can't make water without hydrogen. But there's gonna come some point where technology can only go so far. Because, all right, we've got a hydrogen atom and or 2 hydrogens and an oxygen just chilling out here. Oh no, there's not enough room. All right, we have to split off the hydrogen, and now we got a monohydroxide, and that's what we need instead of using water. I don't know. The future's crazy, man. All right, ultra pure water serves 4 primary semiconductor applications. So what do we need this ultra pure water for? Wafer cleaning and removing particles and residue and surface contaminants. So before you press that next wafer on top of that other wafer, every little particle, little bit of residue, anything, contamination must be cleaned with this ultra pure water. And that's, if my ultra pure water isn't perfect, it won't be perfect when they get squished together and they're making the wafers, stacking the wafers. All right, the ultra pure water is also used for chemical mixing. Provides an ultra pure base for photoresistant and etchant preparation. What is this? I think it's like etching. What is that? Formulating a pre-mixing chemical solution, usually acids and bases or salts, selective removal. So like dentistry, your semiconductor manufacturing and dentistry. So you're mixing chemicals. If you use ultra pure water, you're gonna get a great, crazy, awesome mixture. All right, say you need 1 part of this chemical and 200 million parts of water, and so you mix them together, and then that mixed solution, that chemical you just created, that combined chemical with the concentrate or whatever the pure chemical is, plus the water, you get the molecular weight or whatever you want it to be. And the chemical is exactly what you want. Well, if that water you mixed it into, or actually you add the acid to the water like you oughter, don't add that. Anyway, it's a thing. So if that water that you're putting the acid into or the chemical into isn't pure, then now you've got chemical plus pure water plus who knows whatever that contamination is. And now you're going to use that to put into people's vaccines, or you're going to put it into, see, now you've brought in a contaminant. So yeah, ultra pure water, you don't want to bring anything into that chemical mixture other than just pure pure, super pure. So that's what you use ultra pure water for as well. So wafer stuff like what I'm going to be doing, and then also chemical mixing for things like chemicals for medicines, pharmaceuticals, stuff like that. All right. Another thing ultra pure water is used for is rinsing after etching and chemical mechanical planarization process. Jeez. What is that? What is that? What's that? Etching and chemical mechanical planarization, CMP, are two fundamental complementary processes used in semiconductor manufacturing to build integrated circuits. All right, so this is outside of my wheelhouse. I make the pure water. This is what that guy needs the pure water for out there on the thing. But I need to understand his stuff. I'm going to be talking to these guys and getting to know these guys because I need to understand how my ultra pure water affects them. So yeah, I'll be learning all about everything so that I know. And then I'm like, oh my gosh, we just got a whole bunch of like tripled the amount of copper coming in. What just happened? I have to understand what's happening out in the factory, what would have caused that, so I can help them help us. You know what I mean? I'm like, why don't we dilute this before it comes back to us so that we can have a steady concentrate that comes into us that we can treat it much fast. You know what I mean? Don't just have these surges of these chemical coming in so we have to keep adjusting, and it's hard to keep track of it. Why not have it go into a buffer tank so that we pull from that buffer tank? So over their full shift, now we've got a consistent, this is what we expect, and we can treat that water. We don't want, hey, at 6 hours into their shift, they do this process and it spikes everything and then it ruins what we're trying to do. But, so I will have to talk to all these other people in the factory to try to get their systems to help our systems. So yeah, this kind of stuff I'll have to be learning. They are two fundamental complementary processes used in semiconductor manufacturing to build integrated circuits. Etching carves microscopic patterns into the wafer. The little lasery thing going like the little paths and stuff for your computers, chips and stuff to be talking through. While CMP smooths and flattens the layers. Etching is a material removal process used to create intricate circuit patterns by selectively removing unwanted areas of material from the wafer. So you get the green wafer, and you're like, I want this path that goes over to this chip, and it's going to have a copper trace in there, but I have to dig this little microscopic, super tiny nanometer, like deep thing into the, and so that's creating residue as you're cutting that little path. And you have to clean out all that residue. That's what the ultra pure water is for the wet etching. Uses liquid chemical entrants to dissolve and target material. So there's wet etching, there's dry etching. It uses reactive gases or plasma in a vacuum to bombard the wafer. It is highly directional, anti-tropic, and crucial for creating extremely thin, precise features for modern complex chips. So what do we use? I can't tell you. Even if I knew, I couldn't tell you because there's an NDA and everything. Anything that, like, I haven't started working there yet. So a lot of what I'm telling you is I don't know. But once I start learning how they do stuff and we have a live stream like this, I'd be like, no. I can just say, this is this. I can't say, this is what we do. I can't say anything like that. I can't tell you what happens there. So anyway, and then there's the chemical mechanical planarization. Is a precision surface smoothing and flattening process. So it's smoothing it out once you've done your traces and you cut it out and you smooth that, whatever. This is for flattening and smoothing. As chips are built layer by layer, the surface becomes increasingly uneven. CMP is required to establish a perfectly flat foundation for the next layer. All right, so you go, you're making your chip, and then it's got to make the next layer. But first, let's go make it all level, then each time that you're planing, see then the word planarization, like you've got a wood plane and you're planing the wood down, you're trimming it all off level. You're creating all this stuff that the water, the ultra pure water, has to brush away and spray away and clean and just make sure it's all gone before you come on and build the next layer. And then it's next layer. But during that whole process, you're using, that's why it uses 1,700 gallons of water for a 7.8 inch square wafer. All right, so we understand. Actually, I'd like to keep this. Can I keep this? I was going to bookmark this and just put all this information in, but I guess I don't need to. All right, so that's another thing you use the ultra pure water for. And then the last one, photolithography equipment, cooling maintains temperature stability. Ooh, is this like, I think that has to do with making solar panels. What does paste mean? Photolithography equipment cooling maintains temperature stability by circulating cooling systems, often with ultra pure water, to keep lasers, optics, and stages at a constant temperature. This prevents microscopic thermal expansion of silicone wafers and machine components using nanometer level alignment accuracy during chip manufacturing. Well, that's super important then. Photolithography equipment needs to be cooled to maintain the temperature stabilities. Obviously. This is so cool. I'm going to be understanding all of this. Like it's all going to be like, oh yeah, it's just normal. A year from now, I'm going to be like, I know stuff, but I can't say nothing. It's going to suck. Oh, my brain. Keep it in, Delnorin, keep it in. This prevents, all right, we're right. The manufacturing of modern semiconductors involves printing billions of microscopic features using light. They use lasers on sharks. Zing! To maintain this extreme precision, cooling systems work in three primary ways. They prevent thermal expansion. As it heats, it expands and then screwed. Materials naturally expand and contract when the temperature changes. Temperature stability ensures that the silicon wafer and the photomask or the rectile, remain this exact same size. Even sub-degree fluctuations, like 0.1 degree change in temperature, can cause alignment shifts and overlay errors. This will ruin the chip. So when you're talking about that 7.8 nano or 7.8 inch wafer that's being made and taking 1,500 gallons, because water is being used to keep the lasers cool. Water is being used for the etching cleaning. Water is being used for the little trace making. Water is being used for, there's a lot of things that need the water to be absolutely perfect. It's not just spraying it down with a garden hose and then slapping on another one with some glue and then spraying it down again. Can you imagine? Oh, heaven's sakes. It's also protecting optical components. High-powered light sources used in deep UV or extreme UV, ultraviolet, lithography generate massive amounts of heat. Precision cooling stops lenses and mirrors from warping, which keeps the light beam sharp and focused at all times. Stabilizing the machine language. The stages holding the wafer execute rapid scanning motions, which generate friction heat. Cooling systems dissipate this heat to prevent the equipment from vibrating. So as, all right. So maybe the laser, I don't know. Does the laser go, like, here's the wafer. Does the laser go, or does the laser stay still? and the wafer comes in, locks into place, and then the wafer's doing this. And I don't know. It would make sense though that if this was moving, this stabilization, the machines stabilizing the machine stage, the stage holding the wafer, execute rapid scanning motions. So it sounds like the wafer is the one, and then you got all of that rubbing, and you know that's moving it around. You need to keep that all cool. Or do they? Here, let's bust your brain. Let's have this all moving and the laser moving all at the same time. You can like quadruple how fast you can produce a chip. The computer can move as fast as faster than your brain can move. Just have the wafer going and the laser going. Oh, heck yeah! But it's going to be producing lots of heat. Oh man, I'm stoked. All right, in advanced sub 7 nanometer manufacturing nodes, that's back to the less than 1 nanometer. The 7 wafer is at less than 1 part per billion of TOC. And then it would go down to 2 or 3s, and then we're less than, then we're, here we go, below 5 TOC, 0.5 part per billion TOC. All right, sorry, we're still studying this stuff. Oh, cool. In advanced sub 7 nanometers. So that means where TOC is now under a 0.5 part per billion, because that says sub 7 nanometers. This thermal control must operate within millikelvin tolerances, thousandths of a degree. Holy, I said just 0.1 degree and it would be bad. No, that would be really bad. 0.001 degree. Holy cow. Millikelvin is a thousandth of a degree. Oh, this is fun. Tolerance budgets to consistently yield functional high quality microchips. Would you like to know more about the ultra pure water is used to cool these machines, or how extreme ultraviolet lithography? I'm going to not close this tab. I want to go down this rabbit hole later. All right. Did I already? All right, I did. Ultra pure water systems. I want to make sure that edit. Let me edit. Yes, this is this website. I wanted to make sure I bookmarked it here. All right, so now we know about that. Those are the things the ultra pure water in the semiconductor applications are used for. Wow, that was really cool. All right, it's like doing a tour of the plant, you know, just sitting right here. How do ultra pure water systems work? Ultra pure water systems work through multi-stage treatments. Like, remember when the EDI we were talking about that, the electro deionization units, and I said this is just one part of the treatment. There's all these stages. That's what this says. Multi-stage treatment, combining reverse osmosis, and then of course I should have just read it. So I'm blah blah blah, and then I have to read what I just said. Electro deionization, ultrafiltration, and UV oxidization to remove dissolved solids, organics, particles, and microorganisms sequentially. See, dissolved solids, reverse osmosis, organics. Ziggy, stop. My little Alexa thing started answering whatever I was saying. All right, so dissolved solids, reverse osmosis, remove organics, electrodeionization, particles, ultrafiltration, microorganisms, UV ultraviolet oxidization. So this removes that. I want to write that down somewhere. Notepad. Reverse osmosis. Dissolved solids. Then we go to electrodeionization, and that will remove our organics. Then we go to ultrafiltration, and that removes our particles. And then we go to UV oxidation, and that removes our microorganisms. So that was useful. It's like electrodeionization, but it's all one word. But actually, yeah, it is all one word. It doesn't like me to spell it like that. All right. Anyway, let's just minimize that. The purification process follows 3 phases: pre-treatment to produce purified water. So that even before that, we're going to be taking water off the drains on the floor and the collection plates and drains and everything that's coming to us, right? It's not going to be like normal drain floor. There's going to be collection vessels right underneath the wafers that collects all the water they're spraying, and that's going to come back to us. We're not, I surely prayed that we don't. I'm going to have to ask for changes. If some guy spits on the floor, if that is going to make it to the drain, and now we have to deal with the bacteria from his cheeseburger. But I'm going to assume not. All right. So even before it gets to this pre-treatment stage, we've already treated the water, because we're taking a wastewater industrial treatment and then taking out all the copper, all of that stuff out of the water before it even gets to the pre-treatment. So there's a whole bunch happening before it even gets to this stage here. Pre-treatment, media filtration. I'm going to stop the stream in 10 minutes because my wife gets out of work and she has to head off to her other job, and I want to spend some time with her, see how her day went, and whatever. But we're going to stop this in 10 minutes so that I can spend some time with the wife. We might come back with more. I'm kind of thinking that I will do one of these educational videos each day until I leave. We, get in the U-Haul and go. And then I will do another gaming type live stream. So that you get like, oh, and I wanted to do a church one too. All right. So when I come back in a half hour, 45 minutes after this stream, I'm going to do another sermon from the river, whatever that church is there in Bastrop that we've been watching sermons of. We're going to do a sermon video. And so it's going to be like an hour and 10 minutes. And then I'll stop that live stream, and then we'll play a game for a few hours, and then I'll go to bed. So that's what we'll do. We'll do an educational live stream each day, a sermon each day, and then a game each day. All right. So anyway, the 6-stage sequence operates as follows: pre-treatment, media filtration removes particles greater than 5 microns. Carbon filtration eliminates the chlorine, because remember I said you don't want any chlorine going into your reverse osmosis. Reverse osmosis is the next step. All chlorine must be gone before it gets to step 2, or it will just destroy the membranes. Do not let bleach, do not let chlorine gas, do not let any amount of chlorine get to your RO membranes. And water softening reduces hardness. So you throw it through like a water softener, deionization tanks. You want all your calcium, magnesium, all that crap out of your water before it gets to reverse osmosis. Otherwise, your reverse osmosis is going to be like, I'm filled up with calcium, and like on the inside of your pipes in your house, it'll be like, so get all of that out before it gets to your reverse osmosis. Otherwise your reverse osmosis is constantly, like, oh, got to clean it again. We're got to get new membranes in there, and you're constantly, get all of as much crap out of your water as you can before it hits your RO membranes. All right. So you get your hardness down below 1 part per billion or part per million. That your normal water softener in your house can do that. So you're going to put it through like a carbon filter and then through a water softener. Now, if you're in a big factory, that water softener might be 12 foot tall and 6 feet around. If you're in like a car wash. Like you go to your car wash, a lot of car washes with the big arms that come over and the paddle wheel that goes up and over your with the rags flipping around, and though they use water softeners. I installed one. It was up in, I think it was Mackinac City, Michigan, when I was working for Culligan. This is a long time ago, and we installed a water. Nor was it Gaylord, Michigan. You know, I don't even remember where it was, honestly. But it was one of those two. But that water softener, there was two of them. As one is being used, the other one can be being cleaned, and then that one starts being used. This one can be cleaned. But they were 3 foot around and about 8 foot tall, maybe 7 to 8 foot tall. They were huge. Just a normal water softener, or you can have a water softener like it's in your house. It looks like a little 150-pound chlorine gas tank, you know, or argon tank, or whatever your normal gas tanks that you and a welder would have in his shop. You can that's water softener size that you can have in your house. So depending on your application, if it could be a huge factory. Hey, thank you, buddy. Dimitri.
Congrats on getting the job.
Thank you, buddy. Thank you. Appreciate that. So you want to do that, a carbon filter, and you want to do water softening to remove all your calcium, magnesium, blah, 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 blah. And I would put it through another filter before that. And then let it go to your reverse osmosis. And then that's going to remove 95 to 99% of your dissolved solids, reducing total dissolved solids from 500 parts per million down to about 5 to 25 parts per million. So these are TDS, total dissolved solids, not Trump derangement syndrome. TDS is total dissolved solids. So you're going to be measuring that. All right, what's coming out at the end of the reverse osmosis? Is it a 4? Awesome. Is it a 5? Awesome. Is it 7? All right, now it's got to 12. Now it's got to 18. Now it's at 22. All right, let's flip over to the other one. Let's figure out what's going on with this one. Oh, it just needs cleaned. Or do we replace the modules? What's our procedure here? Because you don't want it to get dirtier and dirtier and dirtier. All right, and then from there, it goes into the electro deionization, which is that one video that we already talked about. And that is going to increase the resistivity. Now, there's a measurement that you use in water. One is called conductivity, and one is called resistivity. And they're quite a bit different, and they're kind of like opposites, the way they are measured. One is conductivity, the amount of electricity that or electrical current wants to go through the water, to be conducted through the water. So the higher the conductivity, that means the more impurities are in the water. So your electrical current is going from impurity to impurity to get to the other side of the water. So the more impurities in the water, the easier it is, and the higher your conductivity is going to be. Resistivity, on the other hand, is opposite. How much is that water resisting electric? So if the number is high, that means it's not resisting very well, or low, it means it's not resisting very well. If it is very, very, very almost no particles whatsoever in that water, electric doesn't even want to go through it. Well, to a theoretical level of the 18.2 nano micro, whatever it is. So they're kind of opposites. When you're in a city water treatment plant, conductivity is totally good to use as a measurement. At your home, totally good. When you're on ultra pure water systems, it's not good enough. It doesn't. Resistivity will get you into a whole different realm of precision that that you can't get with conductivity. It's just a whole different layer of fine tuning what your numbers mean. And we ran out of time. All right, I'm gonna shut things down. Stop the stream. We're gonna raid out to somebody. When we come back tomorrow with another. What are we calling this? We're calling this Ultra Pure Water Training with Delnorin. We'll continue from this point. We have lots more to do, lots more to talk about. We have more side tangents and learning as we go along. If you have any questions from watching this stream, jot those down, put them in the comments. make a note, tomorrow's live stream, bring those up, and we can go and we can talk about what you like. Hey, yesterday we covered this. Hey, show. Yesterday we covered this, and you were explaining conductivity, resistivity, and you were kind of weird, like you didn't really know what you were talking about, but you're trying to sound smart. Can you go over that again? Right? And then we can go over it again. So we're all learning, right? Let's do that. All right. So for now, though, I'm going to raid out so I can go talk to my wife. Wife just got out of work, and we've got just a little while before she heads off to her other job. Doom Gnome, I have not raided him in a very long time. So we're going to pick him. I'm going to go over here.
Step 1, pick me.
And raid into him.
Win the game.
You only have 9 players.
You got this.
You can raid? Let's go.
Delnorin, thanks for the raid, brother. Heck yeah, man. Thank you, dude.
Raid?
Yeah, dude, we got raided.
I'm invisible.
Raided.
Invisible.
You are invisible.
He's invisible. He's got a green shirt on.
Invisible.
Hey, look at the camera.
That's awesome. Dude, I love this guy. Outstanding. All right, give him a like, give him a subscribe, give him a follow, all the things. I'm out of here. I'll be back in a little bit, and we will listen to another sermon from the River Valley Church in Barstrop, Texas. And then after that, another live stream where we'll play a game and we'll have some fun. All right, bye everybody. Love y'all. God bless you. Bye.
So proudly we hailed at the twilight's last gleaming, whose broad stripes and bright stars through the